In this lesson, we will prove some theorems about prime numbers. First, let's recall our definitions of prime and composite. A prime number is an integer p greater than 1 whose only positive divisors are 1 and p. An integer that's greater than 1 that is not prime is called composite. Now here's a fact that we're going to use in future theorems. So I mentioned this before, that if a number is composite, it must have more than two factors, more than two positive factors. So if n is composite, then I can write n as a product of two integers, a, b, with a and b both between 1 and n. So 1 is less than a, which could be less than or equal to b, which is strictly less than n. Some textbooks actually have this as their definition of a composite number. Here's another fact about composite numbers. If n is composite, then n has a prime factor less than or equal to square root of n. So you're going to prove this fact for a homework exercise. As a consequence of this theorem, if you're going to check to see if a number is prime or composite, you only have to check factors less than square root of n to determine if n is prime. The first theorem that we're going to prove is the fact that every integer greater than 1 has at least one prime divisor. Every integer greater than 1 has a prime divisor. Let's begin the proof. For the sake of contradiction, suppose that some integer greater than 1 has no prime divisor. So for a contradiction, suppose some integer greater than 1 has no prime divisor. Now consider the set of all integers greater than 1 having no prime divisors. Then this set is non-empty. And the set of all integers greater than 1 with no prime divisors is non-empty. Therefore, we can use the well-ordering principle to say that there must be a least element of this set. I'm going to call that least element n. So by the well-ordering principle, this set has a least element say n, Well, clearly n can't be prime. Why? Well, n divides itself, and so if n were prime, then n would have a prime divisor. So then n is not prime. Otherwise, n would be a prime divisor of itself. So n must be composite. And I can write n as a times b for some integers a and b that are both between n. 1 is less than a, which is less than or equal to b, which is less than n. So a is a positive integer that is greater than 1 and strictly less than n. So since a is less than n, and we assume that n is the smallest integer greater than 1 with no prime divisor, a must have a prime divisor. Okay, so since a is less than n and n is minimal, a must have a prime divisor. Say P is the prime divisor of A. But if P is a prime divisor of A and A is a divisor of N, then P is also a prime divisor of N, which is a contradiction. But P is also a prime divisor of N, which is a contradiction. Therefore, every integer greater than 1 has a prime divisor. Next, we will talk about the Sieve of Eratosthenes, which is actually easier to do than to say. The Sieve of Eratosthenes is a method for finding prime numbers up to a given integer n. Okay, so the idea is we're going to throw out all of the composite numbers and the sieve will only keep the prime numbers. Okay, let me show you how this process works. So suppose I want to find the prime numbers up to a given integer n. So the Sieve of Eratosthenes is for finding primes less than a given integer, say n. Suppose I have a integer that's less than or equal to n. It's called x. So if x is less than or equal to n and x is not divisible by any prime number less than or equal to square root of n, then what can we conclude about x? Well, we can conclude that x is prime. because the fact we mentioned earlier is that every integer n that is composite has a factor that's less than or equal to square root of n. So if you can find a number that's not divisible by any prime less than or equal to square root of n, x must be a prime number. So for a given n, we're going to eliminate from the list of all numbers from 2 through n all the multiples of prime numbers. Okay? So if we can eliminate from all integers between 2 and n, 2, 3, 4, all the way up to n, if we can eliminate all the multiples of 2, because 2 is a prime number, then all the multiples of 3, then all the multiples of 5, and so on, up to all the multiples of primes that are less than or equal to square root of n. Okay, so we continue, and so on, until all multiples of any prime that are less than or equal to square root of n have been eliminated. Then the numbers remaining must all be prime. So let's look at the steps of the sieve. First, we want to write out all the numbers from 2 to n for some particular n that you want to check. Second, begin with the multiples of 2. Since 2 is the first prime number, cross out all multiples of 2. Then the first number that remains is prime, which is 3. So the first number, the first remaining number, is prime. So then we will cross out multiples of this number. Then we're going to repeat this step over and over. After you've crossed out all the multiples of a prime, you go back to the beginning of the list and repeat step 3. Okay. When you go back to the beginning, the first remaining number will be prime, and so then you'll cross out all the multiples of that number. So we're going to repeat step 3 until all multiples of primes less than or equal to square root of n have been eliminated. The remaining numbers are prime. So an example, let n be 30. I want to find all prime numbers less than 30 using this technique. Notice that the square root of 30 is a little bit bigger than 5. It's around 5.477. So in this sieve, we need to cross out all the multiples of any primes that are less than or equal to 5. So I'm going to begin by writing out the numbers from 2 to 30. So the first number in this list is prime. I'm going to circle the prime numbers. So 2 is a prime number. And then I'm going to cross out any multiples of 2. So any other even number in this list is not prime. So I'm just going to put a line through all the even numbers. Okay. So I eliminated all the multiples of 2. The next, now I go back to the beginning, the next number that remains is a prime number, number 3. So now I'm going to cast out any multiples of 3 that have not been marked out. So 6, 9 is a multiple of 3, 12, 15, 18, 21, 24, 27. Okay? Now when I go back and repeat this step, the next number in this list that has not been crossed out is prime, number 5. This is the last prime number that's less than square root of 30. So once I've crossed out all the multiples of 5, all the remaining numbers in this list must be prime. So 5, 10, 15, 20, 25, let's cross that out, and 30. So all the other numbers that remain must be prime because they have no divisor that's less than or equal to square root of 30. So 7 is prime, 11, 13, 17, 19, 23, and 29. So these are all the primes that are less than or equal to 30. The next theorem that we're going to prove, which is credited to Euclid, is the fact that there are infinitely many prime numbers. So the ancient Greeks knew that there were infinitely many primes. There are infinitely many primes. So this is a classic proof that uses the method of contradiction. So for a contradiction, we're going to start off by assuming that there's only finitely many prime numbers. So for a contradiction, suppose there are only a finite number of primes. If there's only a finite number, we could list them all out. So I want to call them P1, comma P2, all the way up to, say, PK. So we're going to assume there's only K prime numbers, and we've listed them all out, P1 through PK. The trick for this proof is to come up with an integer that has another prime divisor other than the primes in this list. So we're going to form the integer capital N which is going to equal the product of all of these k prime numbers. So P1 times P2 times P3 all the way up to PK. And then I'm going to add 1 to this product. Well, since n is an integer greater than 1, we know that n has a prime divisor. I'm going to call that Q. And we're going to show that Q can't be equal to any one of the P1 through PK, and therefore there must be an infinite number of primes, because this is one more that wasn't in the list that we claimed included all prime numbers. So suppose Q equals P sub I for some integer I between 1 and k. So in other words, Q equals one of these prime numbers that I've already listed. Well, if Q equals one of these prime numbers, then Q divides the product of all of them. Q divides P1 times P2 times P3 all the way up to PK. But we already said that Q divides N, so Q would divide any linear combination of N and this product of primes. So in particular, Q would divide N minus the product P1 times P2 all the way up to PK, but this equals 1. So we can conclude that Q, which is a prime number, divides the number 1. But this is impossible because no prime number divides 1. No prime divides the number 1. So we see that Q can't equal one of these primes P1 through PK. So therefore Q is different from all these P1 through PK. But this contradicts our original assumption that we had written a complete list of all prime numbers. This contradicts our assumption that this was a complete list of prime numbers. So we can conclude that there are infinitely many prime numbers. So these last two results, the Sieve of Eratosthenes and Euclid's proof that there are infinitely many primes, demonstrates that mathematicians have been interested in studying prime numbers for thousands of years. In the last 200 years, mathematicians have gone to great lengths to study the distribution of prime numbers, That is, how spread out prime numbers are amongst the composite numbers. So we just saw that there are an infinite number of prime numbers, but they actually get more spread out as the prime numbers get bigger and bigger. So this is one of the key results in number theory describing the distribution of primes, and we'll discuss the prime number theorem, which just describes how spread out these numbers are. But before our next theorem, I want to just review a quick notation about factorials. These types of expressions occur a lot in number theory. So this is n with an exclamation point. It's not read n. We read this as n factorial. And by definition, you would take an integer, positive integer n, and multiply it by all the smaller integers down to 1. So this equals n times n minus 1 times n minus 2, all the way down to times 3 times 2 times 1. So for example, 6 factorial would equal 6 times 5 times 4 times 3 times 2 times 1. So these factorials occur quite a bit in number theory and in counting arguments, a whole branch of mathematics that we call combinatorics, which is counting objects. We see that in permutations, combinations, the factorials arise quite a bit. So we'll need this for the next theorem. So we saw that there's an infinite number of primes, but there's arbitrarily large gaps in between prime numbers. So that's what this next theorem says. For a positive integer n, we can find n consecutive composite integers. In other words, there are n consecutive composite integers. So this theorem proves that there's arbitrarily large gaps between prime numbers. So for any n, any positive integer n, we can demonstrate that there is a gap between prime numbers at least of length n. Here's the proof. We'll construct n consecutive composite integers. So consider the consecutive integers starting with n plus 1 factorial plus 2, so that's the first integer, and then n plus 1 factorial plus 3, n plus 1 factorial plus 4, all the way up to n plus 1 factorial plus n plus 1. So these numbers are consecutive, and in fact they're all composite, because if you look at the factorial part, n plus 1 factorial, that would equal n plus 1 times n minus 1, all the way down to times 3 times 2 times 1. So there's a common factor in the factorial and the integer that's being added to it. So notice that each of these integers is composite because for any k between 1 and n plus 1, k will divide the expression n plus 1 factorial plus k. So each one of these consecutive integers must be composite. So for example, 2 is a factor of this number, 3 is a factor of this number, 4 is a factor of this number, and so on, up to n plus 1 being a factor of that number. Since these are n consecutive integers, they're all composite, that proves the theorem. So there's arbitrarily large gaps between prime numbers. Our next theorem about prime numbers is Dirichlet's theorem on primes in a progression. Now, the proof of this theorem is beyond the scope of this course, but it's a very interesting theorem, and we will actually prove a special case of this theorem. So Dirichlet's theorem says that suppose you have two relatively prime numbers, okay? So if A and B are relatively prime, then consider leaving B fixed and adding multiples of A. So this is called an arithmetic progression. Okay, so consider the numbers like A plus B, 2A plus B, 3A plus B, and so on, 4A plus B. Okay, where A and B are two relatively prime numbers. So this is called an arithmetic progression. Okay, so consider the arithmetic progression of terms an plus b for n equal to 1, 2, 3. So n is a positive integer. So if you look at all the numbers that are of this form, an plus b, then Dirichlet proved that this progression will actually contain an infinite number of prime numbers. So not only are there an infinite number of primes, this is a very powerful theorem that says there's an infinite number of primes that look like an plus b. So the arithmetic progression of these terms contains infinitely many primes. So what we're saying is that the set A plus B, 2A plus B, 3A plus B, and so on contains an infinite number of primes. So as I mentioned, this theorem involves a great deal of advanced number theory, complex analysis, modern algebra. So it's beyond the scope of this course. But we can actually prove a special case of this. Suppose that I let A equal 4 and B equal 3. Okay, so 4 and 3 are relatively prime. Then it turns out we can prove that there are infinitely many primes of the form 4n plus 3 for a positive integer n. So in order to prove that there are an infinite number of primes of the form 4n plus 3, we will need to use the following lemma. If A and B are integers of the form 4n plus 1. So what that means is that I can write each of these integers as 4 times an integer plus 1. Okay, so A and B are both 1 more than a multiple of 4. Okay, so if you take two integers that are 1 more than a multiple of 4, then their product A times B is also of the form 4n plus 1. So if A and B are both 1 more than a multiple of 4, when I multiply A and B, the result will also look like 1 more than a multiple of 4. It'll look like 4 times some integer plus 1. The proof of this lemma will be left as a homework exercise. But we're going to use this lemma to prove that there's infinite number of primes of the form 4n plus 3. Theorem. There are infinitely many primes of the form 4n plus 3. Where n is a positive integer. So the proof of this theorem is very similar to the proof that we used earlier to show that there's an infinite number of prime numbers. So we're going to assume there's only a finite number of primes of the form 4n plus 3, and we're going to form an integer n that will give us a contradiction. So let's begin by supposing that there are only a finite number of primes of the form 4n plus 3. So since there's only a finite number of them, I can list them all out. I'm going to call them P1, P2 through Pk for some integer k. And moreover, I want to assume that these primes are written in order. So I want P1 less than P2, less than P3, and so on, up to Pk. Okay, so these primes are written in order. And then the first prime number that can be written as 4n plus 3 for a positive integer n is actually the number 7, because I can write 7 as 4 times 1 plus 3. We could also consider the number 3 as a prime number of the form 4 times 0 plus 3. So for this proof, I'm going to also let P0 stand for the number 3. Okay. Then, for example, P1 would have to equal 7, and P2 would have to equal 11, and so on. Okay, so for a contradiction, I'm going to form the integer capital N, which is going to equal 4 times P1 times P2 all the way up to times Pk, and then I'm going to add 3 to this. And we're going to show that n has a prime divisor of the form 4n plus 3 that must be different from any of the primes in our list. Therefore, there must be an infinite number of primes. First, notice that I can write any odd prime number has to be of the form 4n plus 1 or 4n plus 3. It's not just true for odd prime numbers, but any odd number can be written as either 1 or 3 more than a multiple of 4. But look at our integer n. Capital N is of the form 4n plus 3. Since capital N is of the form 4n plus 3, then n has to have at least one prime factor of the form 4n plus 3. Capital N must have at least one prime divisor of the form four n plus 3. Why? Well, n has to have a prime divisor, and since n is odd, it's made up of a product of all prime divisors. And if all the prime divisors of capital N were of the form 4n plus 1 by the previous lemma, then capital N would look like 4n plus 1. So since capital N looks like 4n plus 3, at least one prime divisor of capital N must be of the form 4n plus 3. So otherwise, capital N would have the form 4n plus 1 by the previous lemma. So n has a prime divisor of the form 4n plus 3, and we're going to show that none of the prime numbers p1 through pk can divide capital N. Therefore, we can conclude there must be an infinite number of primes because we found another prime of this form not in this complete list. So we will show that none of P0, P1, P2 through Pk divide capital N, and therefore conclude that there are an infinite number of primes of the form 4n plus 3. So we need to show that none of these prime numbers divides capital N, and then we'll be finished. So first I'm going to show that 3 does not divide capital N. So if P0, which equals 3, divides capital N, then 3 would have to divide capital N minus 3, but that equals 4 times P1 times P2 up to Pk. Well, this is impossible. Why? Well, 3 doesn't divide 4, and 3 doesn't divide any of the primes P1 through Pk either. So this is impossible because 3 does not divide 4, and all the P's, P1, P2, up to Pk, are all primes greater than 3. So therefore 3 can't divide the product of 4 and all these P's as well. So we see that 3 does not divide capital N. But Pi does not divide capital N either, for I equals 1, 2, up to K, because if some Pi divides capital N, then Pi would divide capital N minus 4 times P1 times P2 up to Pk. Because Pi would divide N, and it would divide the product 4 times P1 times P2 up to Pk, so it would divide their difference. But this equals 3. But this is impossible because all the Pi's are bigger than 3. So none of these Pi's from 1 to K could divide 3. Therefore, none of the P's, including P0, P1, P2, up to Pk, divides capital N. This is a contradiction because we proved that capital N has a prime divisor of the form 4n plus 3, and therefore this list couldn't be a complete list of all the primes of that form.